Alabama STEM Explorers is made possible by the generous support of HudsonAlpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Holly Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition, Alabama Math, Science, and Technology Initiative.
This is taking way too long. I'll just use this tank instead. This is so much easier. Perfect. Oh. Why did it fly up like that? How was I supposed to know it would do that? Why do some balloons fly up like that anyways? I think I'm gonna find out.
Thanks for joining us on today's episode of Alabama STEM Explorers. I'm Kathryn.
And I'm Anderson.
And Anderson and I are here at Southern Research in Birmingham, Alabama.
I was just telling Kathryn about my balloons. I don't know why one went up and all the others went to the ground.
Oh, I bet you were using a helium tank to blow up the balloon that floated to the ceiling. Am I right?
Well, yes, but why does that change anything?
So it all comes down to density.
Dentistry?
No, density. And since helium is less dense than air, that balloon will float to the ceiling. But a balloon filled with air is going to stay on the ground. Does that make sense?
Kind of, but I don't know what density is. Why does density even matter?
Exactly.
Exactly what?
Exactly, it matters, all matter. So this table, your tennis shoes, the balloon, all matter is made up of density, or it has a certain density. And density is just a characteristic property of something. So for example, this balloon is long and skinny and shaped like a dog, or this balloon is round and circular, or a characteristic property of you would be how tall you are, or that you have the greatest hair of all time.
Thank you. So it's just one way to describe something?
That's exactly right. And so to calculate density, you need to know a couple of things. You need to know the mass and the volume. But here, we can break it down with this example. So what we have in front of us is a car parking lot. That is the square. Got it?
Uh-huh.
All right, so there are a lot of cars in this parking lot. Would you say that the parking lot is full?
Yes.
Yeah, okay, so we can describe this parking lot as, it is a pretty dense lot, okay? But now I'm gonna take some cars away. Has the size of the parking lot changed?
No.
No, but there are less cars in it, and so it is less dense. Does that make sense?
I think I got it, but I'm still not getting it too much.
Okay, well, I have an idea. Let's break it down with an experiment. Do you want to do that?
Yes, please.
All right, let's do it. I love this experiment so much because it's something that our viewers at home can do pretty easily. So all you need are a few cans of your favorite beverage, a fish tank, and your hands. So this is what we're gonna do. Anderson, I have this soda, this lemon lime soda. I'm gonna hand it to you. Do you think this soda will sink or float?
Sink.
Okay, go ahead and put it into the water. Let's see. All right, well, is it gonna float? Is it gonna sink? It is sinking. Interesting. So why do you think it is going to sink?
Because it has a lot of soda in it.
All right, good answer. What about this one? This is a citrus soda. Sink or float? Same size, same shape.
Sink.
Okay, throw it in there. Oh, that one definitely sank. That one down really, really fast. All right, how about this one? Orange soda. Sink or float?
Sink.
Okay, all right, you're getting really good at this. Absolutely, Anderson. You are a smart kid. Is it gonna float? Is it gonna sink? It is gonna sink, ladies and gentlemen. Okay, all right, here we go. Diet orange soda. Sink or float?
Sink.
Okay, try it out. Anderson, you are a smart kid. Oh, interesting. It is floating. Let's try this one. Let's try this diet lemon lime soda. It is also floating. Okay, one more, Diet Cola. Floating. Okay, so why do you think some of these cans are sinking and some of them are floating?
Maybe because of the diet?
That is a very good hypothesis, Anderson. So maybe let's test. Here's a sparkling water. So sink or float?
Float?
Okay, let's try. Let's see. Okay, very good. It floats. So that is really interesting. So the diet soda and the sparkling water all floated to the top. So let's figure out, why does that happen? What's something that we could do to figure that out?
Maybe look at the labels?
Great idea. Let's check them out. So here's a sparkling water. What do you think we can compare on the labels to figure it out?
Sugars.
Sugar. Okay, cool. So let's look. Let's compare. Here's our Sprite and our Diet Sprite. So how many sugars are in the Sprite?
38 grams.
38 grams. What about this one?
0 grams.
0 grams. That's right. And so this experiment is showing you how density works. So the volume of this can of soda is the same exact as this can of soda, but the difference is the mass. And so when you have the same volume but a different mass, the one with the greater mass is going to sink because it is more dense. Does that make sense?
Yeah.
Okay, so I have one more experiment I want to show you. So I want you to close your eyes, Anderson. All right, close your eyes. And I'm going to put 2 sodas in your hand. I'll hold them up here. So, yep, all right. And now I want you to tell me which one is heavier.
This one?
That's right. Open your eyes. Yeah, that is right. So the root beer is definitely heavier than the diet root beer. And if you don't believe me, try it at home. You can really tell a difference. And it's because the amount of sugar that is inside these beverages. Does that make sense?
It does.
All right, so you are getting pretty good at this. I say we do one more experiment to test your skills.
Okay.
All right, so the last density experiment that we are going to do, it seems like a little bit of magic, but really it's just some pretty cool science. So what we have here is we have a candlestick that Anderson broke earlier, and you can go ahead and tell the viewers at home it is a real candlestick, right?
Yes, it is definitely a real candlestick.
All right, and so what we're gonna do is we are going to make predictions, and we are going to see if the candlestick will sink or float. So Anderson, I would like you to drop this into that beaker. Is it gonna sink or float?
I think it'll sink.
Okay, why do you think that?
Because it's bigger.
Okay, good idea. Let's throw it in there. And it sinks. He's a pretty smart kid. All right, you want to throw this one in the other beaker, sink or float?
Float.
All right, why do you think that?
Because it's smaller, so it'll weigh less.
Okay, well, let's check it out. Let's see. It floated. You were absolutely right. Okay, so those were good answers. Now let's see what will happen if we take this big candlestick and we put it over there.
It's floating.
It's floating. Now what if we put this little one over here? It is sinking. What could be going on? Let's think about this. So the candlesticks are the same, right? They came from the same candlestick. They're just smaller pieces. And so what that means is that the density of both pieces of candlestick, they are the same. They are the same, right?
Right.
So why would they float in one beaker and sink in the other beaker?
Maybe they're different solutions.
That is a great hypothesis, Anderson, and we can test that hypothesis by calculating the density of the solution inside of our beakers. So I'm going to take these candlesticks out. There we go. Now we have a scale right here, and so the first thing that we need to do, we only want to calculate the mass of the solution. So we are going to tear the scale or zero it out. Just press that button right here. Okay, perfect, good job. And now when we weigh our beakers, it will only give us the mass of what is inside. So we are gonna weigh this beaker, and it says it is 1,000 grams. So this one has a mass of 1,000 grams.
Okay.
And a volume of 1,000 milliliters. That would give us a density of 1 gram per milliliter. And you guys might know this, but that's water. So water has a density of 1 gram per milliliter. Second beaker, what is our mass for this one? What is the solution's mass?
786.
That's right, 786. So the mass of this is 786 grams. The volume is 1,000 milliliters. So that is going to give us a density of 0.786 grams per milliliter. So the densities of the solution are different which is why our candlestick floats in one and sinks in the other. Does that make sense?
Yeah, it's starting to.
Okay, great. So does it kind of tie back to the balloon? Are you starting to understand why that balloon went up into the air?
I think so.
Okay, great.
Hi, my name's Kennedy, and I want to know, why are bubbles round?
Scientists refer to bubbles as minimum surface structures. This means that they always hold a gas or liquid inside of them with the least possible surface area. The geometric form with the least surface area for any given volume is always a sphere, a round shape. Bubbles are round when they float free through the air, and individual bubbles will always be round. But when bubbles attach to one another, they could create all sorts of shapes.
I got interested in construction growing up. I grew up on a farm in New York, and when I was a little kid, they built a big pole barn out at our house, and I was just fascinated by that. After that, I studied mathematics and some technology stuff in high school, and those teachers really encouraged me to kind of chase that dream. After that, I went to Auburn University, and I have a building science degree. I use STEM every day in my job. I'm a chief pre-construction manager, and so that job is putting together a team of estimators to figure out how much a construction project like this is going to cost. I work with engineers and design firms throughout that process, and we work back and forth together trying to figure out what we're building and how much that's going to cost, how long it's going to take, how much equipment we need. In order to do that, like I said, the design team usually uses design software, and I use estimating software to do that. So there's a lot of computer back and forth, drawings, 3D software, but also engineering, figuring out how big the crane needs to be and things like that. I often work with high schoolers who are interested in construction, and what we try to encourage them is to continue on in their high school career with their mathematics. If you want to do what I did, engineering, a lot of the people I work with study engineering. I just studied building science. It's a lot of the same things. So just staying with your sciences and your maths and continuing on, because you know what we do every day, while it does involve a lot of math and science, we're not sitting at a desk every day all the time. We work in teams. It's exciting to pursue a job. It's also exciting to get to build a job. It's fun to come out here to the job site and see what you saw on paper or in a 3D plan come to real life, and know that someday, you know, somebody's going to be in a doctor's office here. If this is a career you're interested, you can go really far in this world, and the jobs that you can do are varied. You can be a superintendent, you can be a pre-construction manager like me, you can be a project manager like others you've seen, and there's just kind of the sky's the limit in this career.
Hi, I'm Neil, and Nilah and I are here at the HudsonAlpha Institute for Biotechnology. Nilah, can you take these 6 blocks and make a stack of them?
Yes.
Excellent. Thank you very much. Now, can you take these 7 liquids and stack them for me?
How would I do that?
It's a little tricky to stack liquids, isn't
Yeah.
it? But we're going to actually use a property of these liquids called density. Now, density is a measure of how much of a substance is packed into a specific area. In scientific terms, it's a relationship between the mass and the volume of an object. Okay. And it's a property of everything. Each thing has its own density. We can take advantage of liquids that have different densities because they will stack on top of each other with the heavier densities at the bottom.
Okay.
So we're going to start. I've already put honey in the container. Honey is our most dense of all of our liquids.
Okay.
Next, we're going to start with corn syrup. So pour that in. Just pour it right straight down the center. Try not to touch the sides. I love this activity because you can do this at home with things that you probably have in your pantry. You just have to know the specific densities. All right, good. And so now you can see that we've separated out. We've got our lighter layer of corn syrup and our darker layer of honey. Okay? How about blueberry syrup? All right, excellent. Dishwashing liquid. Okay. All right. You're doing a great job. Not getting it on the side. Okay, now we're going to work with water. And water is a little tricky. We want to make sure that we don't mix it. So instead of pouring it straight in, we're actually going to use a turkey baster.
Okay.
And so you're going to actually get the water, and then you're going to set it right above where the syrup, the dishwashing soap is, and then squeeze it in, okay? Right along the glass, that's right. Okay. Go ahead and finish that one off. That's good. Doesn't have to get all of it. Okay. Now going ahead, we're going to next do the cooking oil. And we know that oil and water don't mix. That has nothing to do with their densities. They're just substances that don't mix. So you can actually slowly pour this in along the side. I'm going to rinse out the turkey baster while you do that. Okay, now the layer that's going to go on top is rubbing alcohol. That's our last one, and you can use the turkey baster, and again, try to have it go down the side of the glass. And do that one slowly. You do not want it to mix with the layers underneath. There you go. Great. Okay. So what you've managed to do quite nicely is stack all of these liquids going from our heaviest, most dense, all the way up to our lightest. So we've got 1, 2, 3, 4, 5, 6, 7 stacked layers. Really nice.
Yes.
Now what we can do with this, because we know what these densities are, there we go. These happen to be all the densities. Mm-hmm. We can now take things where we don't know the density.
Okay.
And we can see where they land. So why don't you take that cherry tomato and drop it straight in. Drop it just right, go a little closer to the surface. All right, now drop it in. Let's see where it goes. It's a little tricky to see, but it is actually right here between the dishwashing liquid and the water. So if we look over here, our cherry tomato's density is between these two. Mm-hmm. Why don't you try this screw? Okay. Let's see what it does. All right, so it has settled. It's floating right in between the corn syrup and the honey.
Yes.
So we know that the screw sits right here. All right, how about this one?
Okay.
Yeah, this is full of air, and it's buoyant, so it's going to just float up on top. And then last, let's try that nylon bead that you've got. And that nylon bead has stopped between the dishwashing soap and the blueberry syrup. Okay, let's actually calculate the density of our honey. Okay. So I've got a container, I've got 10 mils of honey in that graduate cylinder, and we've got a balance here that'll measure. Now I've already set the balance in such a way that the balance actually is going to subtract out the weight of the graduate cylinder. So Nilah, go ahead and put that on top of the balance. All right, and tell me what it measures.
31.32 grams.
Okay. The formula for density is mass over volume. And there's our mass.
Okay.
And then what's our volume there? How many, can you read on the graduate cylinder how many mils we have?
We have 10 mils.
Okay. All right. So I just realized that I forgot to actually take out the weight of the cylinder when I plugged the mass back in. So that's okay, because what we're going to do is we'll grab another cylinder and we'll weigh that, and then we'll subtract that out. I actually know that the weight of those cylinders is enough that actually when I subtract out the cylinder, I should get about 14 grams. So we're just going to assume that I've actually done that. Science doesn't always work the first time you try something. And so what that would be 14 grams over 10 mils, which is 1.4. And that's about the density that we know our honey is.
Okay.
So you could actually do that with every single one of these different pieces. So you stacked our blocks. You stacked our liquids. We figured out our individual measures. You can try this at home with lots of different things. You can try different kinds of cooking oil. You can try different types of syrup from the store and see if they actually all have the same density or not. This is a great activity to just explore the relationship between the mass of something and its volume. All right, so that's it. Well done on our stacking in both directions, Nilah. You did a really fantastic job.
Thank you.
Nice work.
My name is Bernetta Woodbury. I am a project manager for Brasman and Gorey Construction Company. I have a civil engineering degree from the University of Alabama. I became interested in construction when I was in the 7th grade. My dad, as a hobby, used to build things out of wood. So one night he decided he wanted to raise my mother's living room floor. So overnight we had raised the floor. So from there I learned that I wanted to go into construction because I like to watch nothing become something. In my job every day, I like to use my technology to come up with looking at drawings and coming up with what's the best way to make sure we build the correct thing on the project. I use STEM every day in my career of construction for the technology side and the mathematics side. On the technology side, we used to make sure we're efficient in building what we need to build. Our drawings are all on iPad, so we use that to check drawings and I check what we're actually building in the field. I use the mathematics side a lot because I manage the money that's given for the job. I use it more like a checkbook. I'm given a certain amount of money to use and use out right contracts and stuff to stay within that budget to make sure we spend the money that's needed to build the job. So I'm constantly working with the money side with my subcontractors and my team that I'm working with. My advice to a young person that's coming up would be find something you want to do so you don't have to work a day in your life. One reason I chose my career is because I like watching nothing become something, and to be able to go to a job site every day and see how it develops. One of the projects I'm working on now or finishing up is the stadium. So I was able to go out there when it first started and to be able to watch that particular project unfold into something that I could drive by and go to and be able to watch a football game in the future. So that's rewarding to me. My name may not be on the building, but I can say I helped build that. And that's one thing I can say, when you find a career that you love to do. Find a career that you feel that's rewarding to you, no matter what that career is. Because once you find that, you'll never have to work a day in your life because you enjoy going to work every day.
Thanks for watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of HudsonAlpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.